Antarctica. Thousands of miles above that frozen landmass, modern satellites pick up something even stranger. A massive heat signature trapped beneath the ice. No geological explanation. Just heat. Circular, still and unexplained and buried deep inside. Physicists uncover something they never expected to find. Lines of error-correcting code. The question is no longer what lies beneath the ice, but whether this entire world from the deepest core of the Earth to the furthest particle in space is part of something else entirely. Real scientists are now trying to prove it. And if they succeed, then nothing about this world will ever look the same again. The code beneath reality. It started as a theory. What if everything we know is a simulation? Physicist Brian Cox, in a conversation with Joe Rogan, shared his thoughts on the subject. They're moving through space. They're still there. And if you go across that horizon, then you are going to the center. While he didn't outrightly claim that we're living in a simulation, what he described sounded almost indistinguishable from one. According to him, most scientists are leaning towards a strange possibility that space and time themselves might not be fundamental at all. They might be emerging from something deeper. And that deeper layer, he said, starts to look a lot like a quantum computer in structure, in behavior, and in how the universe appears to function. If reality behaves like a quantum computer, processing, calculating, updating, then it opens the door to a disturbing thought. Maybe the universe isn't just strange. Maybe it's constructed. The universe looks in some ways like a giant quantum computer, which is not to say that we live in a simulation. The universe looks in some ways like a giant quantum computer, which is not to say that we live in a simulation right before you ask, but it just looks like there's a description of the universe that looks like a quantum computer-type description that doesn't have the concept of space or time in it. Is it possible that is what it is, and that the universe was created? And he's not alone in thinking that. The idea became widely known after Oxford philosopher Nick Bostrom published a paper in 2003. His argument was coldly logical. If advanced civilizations ever gain the ability to run perfectly realistic simulations of their ancestors, then the odds that we're in the real world become vanishingly small. For a while, that kind of thinking lived on the fringe. Interesting, maybe even haunting, but still just speculation. But now, it's different. Scientists are running real experiments. Experiments that could actually test if our universe is simulated. And for the first time, those experiments are returning results that classical physics can't explain. It has found some of these extreme objects. Everything that's out there cause objects to be discovered by our telescopes. One of the most compelling breakthroughs came from physicist S. James Gates Jr. while working on equations related to supersymmetry, a theory meant to unify particles and forces. He discovered something deeply strange. Buried in the math were strings of code, not random strings, actual lines of digital error-correcting code. The same type used in modern web browsers to detect and repair corrupted data during transmission. Gates hadn't set out to find code. He was deep in theoretical math, working through how particles like quarks and electrons interact. Yet, the code appeared anyway, embedded, precise, intentional. This kind of discovery sends shockwaves because it breaks a rule scientists usually trust that mathematics in nature should be elegant, not engineered. Finding digital code in the equations of supersymmetry is like cracking open a tree and discovering microchips, not a metaphor, not an analogy, just code. Real readable code in the math that governs the universe. That discovery stood on its own for years, whispered about in physics communities and conferences. Big Bang is the hot Big Bang, and it's not the origin of the universe in time. It's the end of inflation. But then came something else from a completely different angle. In 2012, at the University of Washington, physicist Silas Bean and his team approached the simulation theory with a more targeted question. If our universe is simulated, what would that look like in measurable terms? Their answer was bold and testable. They proposed that like a video game or a CGI model, a simulated universe wouldn't be infinitely smooth. It would have limits. This is just for the simplest particles that we have emerging from QCD. It's just another level of complexity, and it gets even more difficult. A grid, a resolution. If you zoom in far enough, you'd hit the edges of the pixels, so to speak. Tiny units of space, not continuous, but granular. And if that was true, then high-energy particles like cosmic rays should behave strangely. Specifically, They should move more easily in certain directions, following the invisible grid lines of this simulated space. That's exactly what Bean's team found when they modeled and analyzed the movement of cosmic rays. Those rays weren't spreading out in smooth, random patterns. They were drifting subtly but consistently along preferred directions, as if the universe beneath them had a framework they were snapping to. This discovery echoed something from condensed matter physics. In crystals, electrons move more easily along the lattice structure. The same principle might be happening on a cosmic scale, except in this case the crystal might be the base layer of simulated space. But it didn't stop there. We are living in a universe which is simulated on some kind of a grid structure, and we should look for signatures of that. In 2024, Thomas Campbell, a physicist with experience at NASA and the Department of Defense, launched a series of experiments with one central goal: to catch the universe in the act of rendering itself. His inspiration came from quantum physics, specifically the double-slit experiment, one of the most famous and baffling setups in all of science. In that experiment, particles like electrons or photons behave like waves until someone observes them. The moment they're watched, they behave like particles again, as if reality itself changes when a conscious mind is paying attention. Campbell took that idea seriously. If the universe behaves differently when observed, then maybe it's operating like a simulation engine, one that only renders the full detail of the world when a conscious observer is looking. This might sound wild, but it's a core concept in game design. No video game loads the entire world at once. The graphics engine renders only what the player can see in real time. It's efficient, fast, and saves enormous processing power. If reality behaves like this, collapsing probabilities into fixed outcomes only when observed, it would mirror exactly what's seen in quantum mechanics. So Campbell and his team designed live experiments to test just that, to see whether certain results only emerge when someone's watching. And the early data, strange predictable outcomes, fail to materialize when the system is unobserved. But the moment the experiment is viewed by a conscious mind, things change. The results collapse into clarity, just like a simulation locking in the next frame of reality. Now taken separately, these experiments are each fascinating, but together they begin to form a pattern. None of them are using science fiction. They're not guessing. These are peer-reviewed papers, reproducible studies, and live data that suggests something unthinkable. That the universe may not be a continuous natural system at all. That it may be rendered, structured, programmed. Even the famous Planck length, the smallest possible unit of space, seems to support this. In current physics, space itself is not infinitely divisible. There's a hard floor, a pixel, something that cannot be made smaller. And what's more, time too appears quantized, flowing not smoothly, but in discrete ticks. In computing terms, that's a clock cycle. This grid, this clock, this limit on resolution, all mirror how digital simulations work. Every frame rendered, every action is processed. Every state is observed only when necessary. And suddenly, the weirdness of quantum mechanics begins to make more sense. Why does an electron exist as a cloud of probability until it's measured? Why do particles instantly affect each other across space? As if the rules of distance don't apply in a natural world, these are paradoxes. But in a simulation, they're features. There was no need to model every inch of space, just the parts the user can see. And in that light, the pieces start to connect. Supersymmetry equations contain code. High-energy particles show grid-line behavior. Quantum systems render outcomes only when observed. While most scientists are cautious, even skeptical, none of them can explain these findings away. Physics, long the engine of certainty and materialism, is now finding the edges of something it cannot fully grasp. Because if this is a simulation, the most obvious question becomes, what else has been programmed in? And there's a place here on Earth that might hold a clue. A place where the impossible seems to be showing itself. Antarctica. Far from the labs, away from quantum equations and theoretical grids, lies the coldest, quietest place on Earth. Antarctica, a continent larger than Europe. Over 98% of it, hidden beneath a frozen shell so thick it could bury mountains. It's a place untouched by cities, untouched by time, a place that holds secrets so deep, not even sunlight has reached them in millions of years. And in one part of this frozen continent, something is wrong. They move really slowly, though. They deform under their undergravity, just like a pancake batter. When you pour it on the pan, it kind of slides out towards the edge. In a remote region called Wilkes Land, satellites picked up something strange. Not just a temperature spike, not just a blip, but a massive persistent heat signature buried beneath miles of ice. And it didn't come from surface readings. It came from space. The anomaly was first detected by NASA's GRACE satellites, twin spacecraft launched in 2002 to map subtle shifts in Earth's gravitational field, continuing the legacy of the GRACE mission of tracking the movement of water across our planet. They don't use cameras. They use precision gravity measurements. As they orbit the planet, they measure how one satellite pulls slightly ahead or falls behind the other. Tiny changes caused by variations in mass below. When the satellites passed over Wilkes Land, they recorded something startling. A massive gravitational anomaly hundreds of trillions of tons heavier than the surrounding crust. A mass concentration buried deep under the ice, roughly 300 miles wide with no visible surface activity, no mountains, no crater, no volcanic field. And the gravity wasn't the only strange signal. Subsequent studies found a large amount of geothermal heat rising from the same area enough to melt ice and change the landscape, but it didn't match any known volcanic system. The heat flow pattern didn't behave like magma or tectonic uplift. It came from nowhere and it made no sense. Researchers used ice-penetrating radar and seismic mapping to learn more.